Hello everybody, and welcome to the top of page 142 in the workbook. And this is kind of the second half of this very long section 6.2 that we're working through. To motivate this next definition that we're about to talk about, I want to think about a problem that comes up in statistics a lot, the idea of the least squares problem. And this is a technique for taking a set of data points and trying to come up with a best fit line through those data points. And have you ever wondered where the formula for doing that comes from, or how your calculator calculates a least squares line? Okay, well, there are different ways to come up with it, but one way is to use inner product spaces. And to do that, the concept of orthogonality and projections, vector projections, is very important. Okay, so that's where this definition that we're about to talk about is leading, and then the very last section of the course will specifically return to this problem of least squares. Okay, so let's get started here. So starting with the definition, let's suppose that we have a non-empty subset in an inner product space. So we've got a vector space with an inner product. And we're going to define something called S perp. Okay, that's perpendicular sign that you see is red perp, P-E-R-P. And by definition, that set is going to be the set of all vectors that are orthogonal to every vector in S. Okay, so specifically, if we write that out in mathematical notation, S perp is the set of all x and v such that the inner product of x and y is 0 for every y in S. Just saying what we just said. Okay, S perp is the set of all vectors that are perpendicular to everything that's in S. Okay, and we're going to give this set a name. It's going to be called the orthogonal complement of S. Okay, and just to get a feel for this definition, I'd like to take a couple of specific sets and see if we can sort of reason out, just informally, what S perp would be for these sets. So starting with part A here, okay, suppose that we take S just to be a one-element set. It's going to contain the one vector 1, 1 in R2. What would S perp be? Okay, well, by definition, it's the set of all vectors that are perpendicular to everything in S. S just has one element, so we're looking for all vectors that are perpendicular to 1, 1. Okay, well, one that would definitely work is the 0 vector. Okay, the dot product of 0, 0 with 1, 1 is 0. Can you think of any others? How about negative 1, 1? If you take the dot product of negative 1, 1 with 1, 1, you're going to get 0. And you might notice that any scalar multiple of negative 1, 1 also works. Okay, so this is an infinite set, and if you wanted to describe all of those vectors at once, they all have the form A, negative A, where A is an R, okay, which could be written as the span of just one single vector, 1, negative 1. Okay, what would that look like geometrically? Let's draw a picture of this in R2. Okay, so we started with a single vector 1, 1 in S. Okay, if we sketch that, let's give ourselves a scale here. Okay, it would look like that. And what would all of the vectors in span of 1, 1, 1, negative 1 look like? That's actually a line. Okay, and if we draw that line, it would look like this. Okay, every point that's on this list up here would be on that red line that we drew. That's S perp, and kind of makes sense because you can see that there's a right angle between 1, 1 and every point that's on that line. Okay, so there's our first example of calculating an orthogonal complement. Okay, let's move on to B here. Okay, so this time, what if we started with all vectors in R2 and asked what is S perp of that? Okay, well, S perp would have to be the set of vectors that are orthogonal to every single vector in R2. Okay, how many vectors fit that description, being orthogonal to everything in R2? Think about it for a while. You can convince yourself that there's only one vector that's orthogonal to everything in R2, and that's the 0 vector. Okay, and so it turns out in this case that S perp is just a single vector in this case. Okay, and finally, let's do one more example. Okay, what if we start with a subset of R3 this time, two vectors, 3, 0, 1, and 2, 3, 0, and we want to know what are all the vectors in R3 that are perpendicular to both of those. Okay, well, just to help you picture this, I went ahead and kind of gave you a plot of the two vectors. So V1 is this one, and V2 is this one. Okay, and this is the type of problem that you might have seen in multivariable calculus. What do you do if you want to find a vector that's perpendicular to two vectors? You can actually take the cross product to do that. Okay, so just to review that process, you can do a cross product by thinking of it kind of in a determinant form. Okay, and if you expand this determinant, I won't go through the details, but this would come out to be negative 3i plus 2j plus 9k. And if you drew that vector into the picture, it would be kind of pointing perpendicular to both v1 and v2. And if you think about it for a minute, that's not the only vector that's orthogonal to both of these vectors. Any scalar multiple of it would also be orthogonal. And so if we drew S perp in this case, okay, it would maybe look something like this. Okay, that line that we're drawing is just the set of all scalar multiples of this vector right here that we calculated. Okay, another way to think of this is that that line is perpendicular to the plane that contains v1 and v2. Okay, so if we want sort of a simple description of S perp, we could just say that it's the span of that single vector that we calculated above. Okay, we notice geometrically that that's a line in 3 space. Okay, so there are 3 just brief examples conceptually of how we might think about S perp, orthogonal complements. I want to make one kind of unifying observation with all of these. Okay, if you look at all 3 of the examples one by one that we got, okay, starting with this one, you might have noticed that all of them are subspaces. Okay, we have a theorem way back earlier in the course that the span of any set of vectors is a subspace, and a set containing just the 0 vector, that's a trivial subspace. It fits all of the conditions. And so that turns out to be a general theorem, okay, and a comment that's worth making at the end of this. S perp will always be a subspace. Even if the set that you started with, S, is not a subspace. Okay, so we will continue on with this concept, and it will lead us to a way of approximating vectors in the next theorem.